So previously we spoke about slopes and expressing them as rates of change. And the fundamental question was, it's how do we find the rate of change or the slope at for nonlinear functions. For linear functions it's easy, we have a simple equation, but for nonlinear functions, how do we do it? So let's figure that out through an example. So I'm just going to move this a little above, and I'm going to throw a graph in here, and this is a function. So what I'm going to do is, okay, so this is a function, and the equation of this function is y is equal to 0.2 x squared. So this is a quadratic function facing upwards, and that's the equation. So let's say, for example, if I wanted to measure the slope where x equals 2.5, so right at that position over there. So the slope at that point would be, a line that is, let me just draw that a little better, line that is what we call as tangent. In other words, it's just touching that point. So one way to sort of approximate the equation of that line is to pick another point that is somewhat farther away. So let's pick another point. So I'm just going to use a different color. So let's just say I'm going to pick a point, say at 7.5 over there. Oh, let me just do that. 7.5 over there. And what I'm going to do is I'm going to approximate the slope of the red line by connecting the red dot and the blue dot. So if I do that, I get that slope. So clearly, as you can see, that the blue line is much steeper than the red line. And of course, it's not a good approximation because it's much steeper than the red line. And of course, this happens because we chose a point that's really far away. So what happens if we pick a point that's maybe a little bit closer? So let me pick another point that's somewhat closer. So I'll just use a green dot. So let's say, let me pick, say, this point over here. Okay, and I connect it once again with the red dot and green line. Okay, so a little bit better, but it's still not the same slope as the red line. So it's shallower than the blue line, but still a little bit steeper than the red line. So let me go a little bit closer one more time. So let's pick, say, that point over there, and then connect the dots once again. And we can see, yeah, it's not bad. It's the black line represents almost the same sort of slope as the tangent of the red line. And so we can say that perhaps these two are equivalent, or somewhat close enough to the naked eye that we can approximate that the slope of the red line is perhaps equal to the slope of the black line. Now, how do we do this algebraically? How do we find the exact value of the slope of the red line? We can't obviously approximate. I mean, sure we can, but there must be better methods than this. So let's do this by showing this graph one more time. And what I'll do here is, so I'll get this graph one more time. And what I'm going to do is, first I'm going to express this generally. So let's just say I'm going to take this point here again, and I'm going to call this point, say, x. Okay, and let x represent any arbitrary point. It doesn't really matter where it is. I just chose 2.5 just because we chose that point earlier, but x could be anywhere. It could be here, anywhere on the line. And let me pick another point on this graph. So let me pick, say, something farther away, just for argument's sake. And so I chose it 7.5. And so I'm going to call this point. And so the other thing is, I'm going to say that this point, let me say that it's h units away. So in other words, let's say if x was 2.5, and h was 5, a distance of 5, my point over here would be x plus h. So if x was 1 and my distance was, say, 3, then x plus h would be 4. This x has a y value, which is going to be represented by f of x, and this x plus h value has a y value that's going to be represented by f of x plus h. So basically what I'm going to do is I'm just going to connect these two, and what I'm going to do here is, if you observe, I'm going to use the equation of the slope that we used previously. So in other words, this is, oh, sorry about that. I'm going to use a different color. So I'm going to say this is our change in y, and this is our change in x. And our equation of the slope, once again, was m was equal to change in y over change in x. And we're going to say that this is y2 minus y1 over x2 minus x1. So this is very similar to what we had before when we had a linear equation. So now what is y2? This is going to be our second point. So this coordinate over here is x plus h, f of x plus h. And this coordinate here is x and f of x. So let this be our x. So this is going to be our, pick another color, just pick black again. This is going to be our x2, y2, and this is going to be our x1, y1. This here is a comma, by the way. So it's going to make that a bit more prominent. This is just a comma. It's not x1. It's just a comma. And that's a comma as well. So what this will be is f of x plus h minus f of x over x plus h minus x. And if you observe, the x's actually will cancel out. So what we're left with is simply f of x plus h minus f of x over h. So if you recall, from our previous graph, what happened was, as we got closer and closer and closer, let me just take this one. As we got closer and closer and closer, as we chose points that were closer and closer and closer to the point that we desired, we got a slope that was almost equal to what we wanted. We were trying to find the slope of the red point, and as we chose points that were somewhat closer to the red point, we found slopes that were somewhat equivalent. So what does that mean in terms of expressing it generally? So if you observe that we have our 2 points, x and x plus h. So what that means is, as h is smaller and smaller and smaller, we find a slope, we find an equation of a slope that is almost equal to what we want. So if you think about it just a little bit more, what that means is h has to get smaller and smaller and smaller. In other words, h has to go towards 0. Now, if you think about it, where have we seen this concept where a number goes towards 0? Where we saw this concept before was actually the concept of a limit. So what it turns out is the definition of a slope, the actual definition of a slope, is actually the limit where h goes towards 0 of f of x plus h minus f of x over h. So let's just explore that one more time. So we expressed the equation of a slope as the change in y over change in x, and I just chose 2 arbitrary points on this function, and I called the point that was further away x plus h, and its y value, corresponding y value, was f of x plus h. The initial point that I chose was x, and its corresponding y value was f of x. Now if I express this in a slope function. It was, y2 minus y1, x2 minus x1. Some things cancel out, and I got this expression here, f of x plus h, this expression right here. Now, in order to calculate the slope, we realized that the closer you are, the closer you choose 2 points together, you're more likely to find a slope at the very point that you want, which means that your h value, the distance between your 2 points, which is separated by h, when that distance is narrowed, in other words, where h goes to 0, we get a slope, which is what we desire. And where h goes to 0 is very similar. In fact, it is equivalent to the concept of the limit. So the equation of the slope is merely the limit where h goes to 0 of f of x plus h minus f of x over h. In the next example, we will continue, we will figure out how to do this for nonlinear functions and how to use this definition of a slope to find the slope for nonlinear functions.